All right, here's the official definition of an exponential generating function for a sequence a sub n. The exponential generating function, or EGF, is f of x equal to the infinite series of a sub n divided by n factorial times x to the n. And that's a Maclaurin power series. So, it's very similar to the ordinary generating function. Instead of using a sub n as the coefficient, though, we use a sub n divided by n factorial as the coefficient, which agrees with what we said previously, that the coefficient can be recovered by taking, that a sub n can be found by taking the coefficient and multiplying by n factorial. I'll write that down again in a second. But compare this one to the Maclaurin formula. Remember, the Maclaurin formula has a coefficient nth derivative at 0 divided by n factorial. But here we've already divided by n factorial, so a sub n is exactly equal to the nth derivative, plug in a 0. So let's compare the ordinary generating function and the exponential generating function. And I'll start calling the exponential generating function g of x, just so that it's not so many f's running around. There's the two ways to find a sub n. For the ordinary generating function, you find a sub n by taking the nth derivative, plugging in 0, dividing by n factorial. For the exponential generating function, all you have to do is take the nth derivative, plug in the 0. If you want to find a whole bunch of them using the series command, then a bunch of a sub n's, then you use the series command, and for the ordinary generating function, you just grab the coefficients directly from a x sub n. But for the exponential generating function, if you look at the coefficients, they are the a sub n is going to be the coefficient, but then you have to divide it by, or multiply it by, n factorial. It's already divided by n factorial, so you have to multiply by n factorial to get it back. So it's pretty nice to just keep these handy until you're really used to it, because it's so easy to forget which thing to do for OGF or EGF. So don't feel bad looking back to make sure you remember what you're supposed to do. It's not that much, but it's a not that much difference. But that's the problem. They're so similar. All you have to, if you're looking at the coefficient, if it's an EGF, then you have to multiply it by n factorial to get a sub n. But if you are just finding the coefficient and you have the function, you just plug in 0 to get a sub n of the EGF. To find, there's the functions themselves again, by definition. So it's kind of redundant, but just putting it together, that the infinite sums look like those. And then here's what they're useful for. From the two examples that we have so far, you could probably conclude that the ordinary generating functions are best when it's unordered, like in the first example where it was just the number of solutions to a x1 plus x2 plus x3 equals n. So those solutions would be three numbers for the three variables, but it's just an unordered collection of those three variables. But when you have ordering, like permutations, like pin numbers, the EGF works the best. And then I put a couple of quick little examples to show that they overlap a lot. You find a lot of the same functions, so you have to remember which is which. As in, you have to remember what you're working with, because you can't just look at the function you have and immediately see. Like if you have a sub n equals 1, so that's a constant sequence where it's always 1. Then for the ordinary generating function, f of x will be 1 over 1 minus x. But the exponential generating function, if a sub n is equal to n factorial, you get the function 1 over 1 minus x. That's because of the definition, the n factorials will cancel. And then what if you have, sometimes you can get a nice function for both of them using the same a sub n. For instance, a sub n equals 2 to the n, those powers of 2. If you put that into the ordinary generating function definition, you can collect the 2x and make it all to the n, and then it's 1 over 1 minus 2x. But if you put it into the exponential generating function, it's e to the 2x. So it's very interesting. And what it tells you is that the Maclaurin series for 1 over 1 minus 2x and e to the 2x are closely related. The only difference is that the coefficients of the e to the 2x are found by taking the coefficients of 1 over 1 minus 2x and dividing each of them by n factorial.